welcome here from my side for the next 5G ACA web seminar. Today we have January 26th and I am the moderator for today. My name is Uwe Udenklau from the company Infineon. I'm speaking here live from Munich, and I will give you some information, some background information. And this one is following the first one, which we had January 12th, about testing in 5G ACA. Today we talk about test cases and test beds. So it's called, the first one is called 5G Enhanced Semiconductor Factory Automation at Bosch, where we talk about related to a project, European project 5G-SMART test beds. And we hear today from our two presenters, Leefke, then from Davit. This is the first part, and we have then also a second part which we hear later, but let's come first to the first part. So the second part is then with the speakers about the smart manufacturing, industrial AI services, validation and performance results from Josef from Huawei and Georgios also from Huawei, where we'll see and hear more later. They are both live from Ismaning, it's close to Munich in Germany. And as I said before, we will hear also from the other two speakers which are coming live then from their locations. You should see now on your side an option about the first question, and this is a generic one. I said, which stakeholders group do you belong to? So you can click ICT, OT, academia, or others if you think you're not belonging to them. So please do so. You have roughly 1 minute left, and then you will immediately see the results afterwards on the screen. So please go ahead, click on one of them so that we have also overview who is joining today. Okay, we see now the results. So we have majority, I would say as usual from the last many web seminars, from ICT 40%. However, we have also there quite good interest from OT side, 23%, same to others which are not belonging to the three, and 13% from academia. So thanks for the first one. And I think we will go directly to the next poll so that you're already familiar with it. Now we are asking from which region do you come from? I said, as this is CET morning time, let's see where you're joining from: Africa, Asia, Australia, Europe. Might be majority North America, South America. So please, again, help us to understand where you're coming from. I think we're close now. Yeah. Here we see the results, and as this is CET morning time, as expected, the majority, 87%, coming from Europe, joining from Europe, and the rest from Asia, so 13%, for sure, especially for America, that's in their early morning or even midnight. So thank you very much again for giving us this feedback.
Okay, welcome also from my side to this presentation of the 5G-SMART testbed in the Bosch semiconductor factory. And on this slide, I can show you a bit of the agenda, what you will hear during this presentation. We will start out with the testbed vision and then move on to describing a little bit about the setup and key activities. And then the main focus will be on the progress of the use cases. And for our second use case, you will actually hopefully also be able to see a short demo from this trial site. And then we'll end with a summary and are looking forward to your questions at the end of the web seminar. So let's start with the vision of the testbed. We have developed and implemented this testbed with the ambition to demonstrate, validate, and evaluate 5G for factory automation and intralogistics use cases in a semiconductor factory. And Bosch and Ericsson have been working closely together to realize this testbed. And as we've already mentioned, this activity is part of a larger framework, which is the EU project called 5G-SMART, which does not only contain two other testbeds, but also research and concept development on showing how 5G can enhance smart manufacturing. The clear ambition of this testbed has been to investigate relevant use cases in a realistic factory environment. So this is not something that we are doing inside a lab environment, but directly on the shop floor from this 24/7 operational factory, where we are inside this 8,000 square meter large so-called clean room area. And you can get a glimpse of how it looks like, but you will also see it later on in the demo video here in the pictures, that this is quite a challenging environment to work and operate in. The testbed is operational since 2020 and will officially run until mid of this year, so this is work in progress. Now, let's have a look at the key activities at the trial site. And as said before, we're looking into two different use cases. The first one being an TSN industrial LAN use case over 5G. And the second one, a cloud-based mobile robotics use cases. And both use cases have been developed and are in the use case execution and analysis phase. The third activity to mention is maybe the measurement campaigns that we have at the trial site inside the factory. We run these campaigns to learn more about channel characteristics and electromagnetic compatibility. A few more words about the setup. The 5G network that has been deployed at the trial site for this testbed is an isolated 5G non-public network with a standalone NR building on release 15. And we're making use of Ericsson's indoor radio dot system. In terms of spectrum, we're using the German industry spectrum at mid-band frequency of 3.7 to 3.8 gigahertz. And with this information on the setup, I think we are ready to dive into the use cases, starting with the one on industrial communication. And for that, I will hand over to David.
Thank you, Leefke. Good morning, everybody from Reutlingen, Germany. I will now introduce our first use case, which is called TSN industrial LAN over 5G. At the Bosch semiconductor factory in Reutlingen, a number of industrial devices and different types of industrial communications are used in the production of semiconductor products, such as microelectromechanical systems and various types of sensors used in the automotive industry. In our use case, we consider two types of communication. First, we have communication between controllers. In the plant, we use mostly Bosch Rexroth controllers, which are the ones shown on the top, to perform predictive maintenance and monitoring of various types of industrial machines, which have quite diverse requirements in terms of electricity, compressed air, different types of chemicals, temperatures, and so forth. Essentially, one of the controllers would be connected to a production machine in order to read these parameters, while the other controller would be connected via wired Ethernet network to this first controller in order to collect this information in a controlled manner. And normally, TCP, Modbus TCP protocol would be used for the communication between the controllers. The second type of communication is between an industrial machine and its backend server. This industrial machine is shown on the bottom, and it is used to perform optical inspection of wafers. Wafer is a material that is used in the production of semiconductors, which then serve as a substrate for different kind of microelectronic devices. Essentially, what this device does is to capture a lot of pictures of a wafer and to upload these pictures onto the backend server for post-processing and classification in order to find out whether the wafer is defective or not. And a single machine of this type is able to inspect around 100 wafers per hour, generating roughly 50 megabit per second traffic. The next slide, please. Okay, so the objective of our use case is to validate, evaluate, and demonstrate the applicability of the 5G network for transporting the traffic of industrial LAN applications. And normally in the plant, the communication between the controllers, as well as the communication between the industrial machine and its backend server, is via wired Ethernet network, which incurs high cost in terms of maintenance and cabling. Moreover, it makes the customization of the production cell quite cumbersome. The 5G network, on the other hand, enables us to easily restructure the production cells, moving here and there the production machines depending upon the need. Moreover, it cuts the effort, the cost, as well as the time on maintaining these devices. Furthermore, it curtails the cost on cabling, on installing network switches and network sockets. This picture shows the high-level architecture of the use case. As already mentioned, we have Release 15-based, standalone and fully private 5G mobile network deployment in the production area of the semiconductor factory. This means that all the network components, such as G-Node Bs, the core network, as well as the edge servers, are physically located in the plant. On the top, you can see the controller-to-controller communication. Normally, the controller on the left side, the programmable logic controller A, we call, this would be connected to a production machine to read different parameters. But in our case, it is not really connected to a machine. We instead emulate this traffic with the help of software program running on the controllers. Both of the controllers would be connected to a traffic capture tool. We use Profi-Shark 1G Plus in order to collect the traffic and to be able to accurately estimate KPIs such as uplink and downlink delay, thanks to this time synchronization between these tabs. On the bottom, you can see the industrial machine communication with its backend server. And in this case, the backend server is located in the Bosch network. So as opposed to the controller-to-controller communication, in this case, the communication goes beyond the 5G network. Both the industrial machine as well as the programmable logic controllers are connected to the 5G network through a 5G industrial router that is based on Qualcomm X55 chipset. In terms of the current status of the use case, we have almost finished the integration of the use case into the 5G network. We have defined the KPI as well as the validation scenarios for this use case. The next slide, please. Now, just to give you a little bit of insight into what we are testing, what we are interested in testing. So I will briefly introduce a couple of validation scenarios. In the first validation scenario, we have a controller-to-controller communication over the 5G network, and we don't have any other kind of traffic in the network. So here, the objective is to calculate the efficiency of the controller, which is defined as the total number of successfully transmitted packets over the 5G network divided by the number of packets transmitted over the wired network. And so this is something that depends on the uplink and downlink delay. Normally, a mobile network deployment in a factory would be shared between different field devices such as 5G-enabled automated guided vehicles, 5G-enabled programmable logic controller, and various types of production machines. Therefore, in the second validation scenario, apart from the controller-to-controller communication, we also consider background traffic in the network. And as a source of background traffic, we use iPerf tool. So here, the objective is to evaluate the impact of the background traffic onto the controller traffic. This is done by gradually increasing the background traffic in the network and estimating the efficiency of the controller communication. So what is important to mention here is that both the controller traffic as well as the iPerf traffic have the same default priority in the network. The next slide, please. So in the third validation scenario as well, apart from the controller-to-controller communication, we also have iPerf traffic in the network. But as opposed to the previous scenario, however, we first prioritize the controller traffic over the iPerf traffic, then we start testing essentially the same use case. So what we do again is to gradually increase the background traffic in the network and to evaluate the impact of the background traffic, in this case, onto the prioritized controller-to-controller traffic, hoping that in this case, the impact would be much less. Finally, in the last scenario, we have industrial machine communicating with its backend server. Then apart from this, we also have iPerf stream. So the objective in this case is to increase the background traffic in the network and to evaluate its impact onto the performance of the industrial machine. This concludes my presentation. Thank you very much for your attention. Now back to you, Leefke.
Thank you, David. Now we move over to transportation in the semiconductor factory, and to set the scene for the intralogistics use case that we have, we've collected on this slide a few points on how transportation looks like in the factory today. So already today, transportation of material is partially or fully automated in the factory and is quite an essential part of the production. There are around 20 mobile robots operating on the factory floor, and this number is expected to increase as well. At the moment, the mobile robots are dispatched centrally, and then they are loaded with their task, and then they are going to execute the task. But a number of issues arise with mobile robots on the shop floor, and some of the examples we've noted on this slide in the corner of the left side there. As you can see from the figure, the clean room is very densely packed with equipment, and the corridors where mobile robots and humans have to interact are very narrow. So coordination issues can therefore be a problem. For instance, if you have two mobile robots that encounter each other, they can kind of start to dance with each other instead of being able to pass by each other. Second issue is inefficient path planning. All robots have their own map, but an obstacle encountered by one robot cannot be added to the map of the other robots. So all of them have to discover the obstacle in order to place it into their maps. Software management is also rather cumbersome, with robots having to be assessed individually for updates. So what are the ambitions when it comes to 5G enhancements that we have? Well, we want to increase the dynamicity and flexibility of the robots. We want to make the fleet management more energy and cost efficient, improve the mobile robot software management, and make transport control more efficient. So now let's have a look at how this is supposed to be made possible on this slide. So here we can see in the figure on the right the architectures of 3 different mobile robots. And I will now slowly walk you through this figure to explain what we mean when we say that we are re-architecting mobile robots. So in the figure, you can see that there are 3 columns, where the first one is for a typical commercial mobile robot. The second one, the architecture for a commercial mobile robot that we have enhanced with 5G. And the third column, the architecture for a 5G enhanced research mobile robot. And then you can also see a dotted line in the middle, and that denotes the split between architectural elements that are implemented on the robot platform itself, which is everything below the line, and the architectural elements implemented in the factory cloud, which is everything above the line. So if we now start with the column to the very left, we can see that the architecture of a commercial mobile robot, state of the art, means that basically all functionality is implemented on the platform itself. Some very limited fleet control is possible from the cloud. And now when we are re-architecting this mobile robot, we mean that we are now removing more and more functionality and control from the mobile robot platform itself and into the cloud. And the first way we do this is by taking this commercial mobile robot and try to implement as much as possible functionality in the cloud. In our case, we've succeeded in moving navigation, trajectory planning, and collaborative fleet control from the device into the cloud using also a common map in the cloud. But coming from research, we are also looking into the extreme case, which is shown on the very right, and that is the 5G enhanced research mobile robot. This is not a commercial robot, but a robot that has been built up from scratch for the testbed and for which basically all functionality is moved into the cloud. For instance, the control of the servo motors of the wheels. And one additional aspect that we want to investigate with this research robot is how even safety functions could be supported from the cloud. And as you can imagine when looking at the figure, when moving critical functionality from the robot itself into the cloud, this communication link between the robot and the cloud becomes very important and should support low latency and high reliability communication as supported by 5G. Now, before showing the demo video, let me first of all introduce you to the 2 mobile robots that we investigate. So in the picture, you can see to the left, the commercial robot that we have enhanced with 5G, and to the right, the 5G enhanced research robot. And really to see how this new control from the cloud improves factory automation, we are evaluating a number of factory production KPIs, and some examples are shown here. For instance, we want to look at measuring reaction times in order to see the impact on productivity. We determine the number of lost connections or handover failures in order to get an idea on the impact on quality. We measure collisions and emergency stops, which give us an input on possible safety-related improvements. And we're also looking at battery lifetimes to see the impact on sustainability. And as for the industrial communication use case, we have a number of different demo scenarios to measure the KPIs that have been mentioned. And now in the following demo video, you will see some of these demo scenarios. And in particular, you see how the common map is created, how the two robots coordinate with each other, and for instance, how the common map is used. And keep in mind when watching the video that for both mobile robots, but in particular for the research robot, the black one, a significant, if not all, amount of functionality is operated from the cloud.
First scenario is map creation. Here you can see how the AGV creates a map in the factory, so it scans its environment, and this map will be used as the basis of the common map in the cloud. Second use case is obstacle avoidance. Here you can see how AGVs react to sudden obstacles. In this case, humans. You can see the research AGV is quite agile, so it tries to avoid a collision and replan immediately. In another execution of this use case, you can see also the video from the onboard camera on the lower left corner. And we can say that even though every control component is running in the cloud, it reacts quickly to obstacles and replan its path. Route intersection. Here the problem is that the routes of the two AGVs cross each other, so there should be some solution. How to handle that? So in our fleet manager, we handle the situation by giving priority to the AGV that is already in the intersection. So in this case, the commercial AGV was there first, so the research AGV stops. This is the case in the second execution of this test, and also it waits until the commercial AGV goes, and then it continues its trajectory towards the destination. Navigating on narrow corridor, it's another relevant use case. So you have to solve the problem, and the AGVs are going towards each other, and one AGV should move from the way so the other can continue its mission. And then of course in this case we selected the research AGV because it is maneuvering much better in this narrow environment than the commercial one. And here this is another execution of this use case, and here the research AGV moves to the left and let the other one go. Of course, after that it will also continue its mission to the target location, as you can see now on the video. Using the common map is one of the key use cases. Here the task is that the commercial AGV should go to the green dot on the map and the research AGV to the red dot on the map. So they both plan their trajectories and starting executing them, but the commercial one detects an obstacle and put it in the common map. So both AGVs replan actually. Even the research AGV who didn't see this obstacle, and thereby saving significant travel time and distance. Thank you very much for watching this demo, and please contact us if you have any question.
Now, I hope this demo was interesting for you. And now, before summarizing this presentation, let's have a quick poll with a question on this slide. Question is, when do you see first 5G use cases being implemented in your industry? 3 choices, don't know, in less than 5 years or less than 10 years, hopefully not beyond that. And I think while you are thinking and providing your input, I will use the time to summarize a bit. So I hope we have provided you some insights into this 5G ACIA endorsed testbed that has been built up to validate the applicability of 5G in the automation of the semiconductor factory. The requirements of the use cases investigated are very strict and call for reliable low latency communication as supported by 5G. In terms of benefits, I think we've seen a couple of them. Examples are the increased flexibility, easier software management, simplified maintenance, etc. In this presentation, we have, of course, only given you the latest status of the test, but this is work in progress, and we will be ready with results in June 2022. So if you want to stay up to date, you are welcome to connect via our website, LinkedIn, or Twitter. And I think with that, we thank you for listening, and I think I'm handing back to you now, Uwe.
Yeah, as said, you see also the poll which was done there, the third poll. So yeah, majority is below 5 years, so less than 5 years, which I think is a good sign. So
yes, agree.
Thank you very much, everybody. And I think we move now to the second one, I guess.
So, hello from Ismanik Munich, from our Open Lab. I am here to give you a short overview of the testbed, which was endorsed by 5G Akia last January. It actually includes 3 use cases. The first one was about 5G-enabled mobile quality control. The second one was about preventive and predictive maintenance. And the third one about safety on the factory shop floor. We have started working on the first use case since last year, and we presented the first results last September. This testbed is unique in a sense that it includes not only validation, but also performance measurement of new solutions. And we also try to achieve some thresholds in the performance by optimizing the network, by testing different equipment. We are also very happy to announce that Basler, who has just joined in January this month, joined officially 5G Akia as a member, has onboarded our testbed as a technology partner. And they have provided some new equipment. You can see here the new camera, this ACE2 Pro camera, which has been now included in the testbed, and we do also some comparative assessment versus the results we got before. I will give you a short journey about what is this use case about. Practically, we want to optimize the idle transport time by doing some mobile quality control and visual inspection with machine vision and AI of the finished product, and then make some decisions based on the outcome of this analysis. So you can see here our targeted KPIs. You can see the Basler camera, and you can also see our OT network. In that we will later on also we will have a kind of live streaming also from the Open Lab, and you will experience it live. So here is an overview of the production line. 7 stations. The first station is for customization, then incoming warehouse, then this is the actual production of the USB sticks. Then the fourth part is the data injection, the software which is injected inside the USB stick. Then it's the outgoing warehouse where you have the output of the product that is sliding on the bay, and then the robot, the AGV with the robot is coming with the Basler camera to analyze if it is good or bad, and then move on to the delivery station for packaging or for a different station for disposal or rechecking by a technician. Josef later on will explain that we have also included a new element here, which is Profinet over 5G. There is different control layer for the AGV itself and different service for the mobile eye for the quality inspection of the camera. Okay, a little bit more detail here. I don't know if you are coming, it is coming on your screen. The different steps of the process. Is it right? Is it on screen? Okay. Okay. So in first step, you have the creation of the order. Somebody is inputting the details that they would like to have on a sticker, which is going to be printed on top of this USB. Then the customization according to the details, and then the order is released so that the product, the raw product, is going to be selected and proceed into the production. The second step is a quality check of the slot alignment of the USB stick. In case it is in the wrong direction, then there is a warning. If everything is okay, the product is set to production by swapping it into the right direction. So let's see a short video of how this is working in practice. There was a lot of background noise, so I have muted it. So you see there, the USB stick from production is printed. Here a sticker will be put on top, and then it will be delivered to the station number 4. It will be rotated. You will see here that the USB will be sliding out, here where my cursor is. And then it will be delivered to the next station for the data injection. Having said that, we sometimes experience some issues when you have not a correct printed sticker, or you have 2 stickers printed instead of 1. This is also an element of the preventive and predictive maintenance of use case 2. We are going to analyze what are the conditions, what this is happening, and hopefully we'll correct this and find also an alternative way to fix it. So after this product is finished, it's sliding on the bay for the robot pickup. I hope you can see also my second video now. Is it okay? So you see here the AGV is moving to the pickup area. Station number 5, which is the outgoing warehouse, you have the product buffering. You can see also the slots here with the products which have been delivered from the production line. Now the correct one is coming, and it is delivered to the bay, so that the robot with the mobile eye will do the quality check and then the pickup. Different scenarios here. You can also have it as a mobile eye, perhaps in a hazardous environment. You can send it instead of a technician, and also to have this educated decision with a trained model we have. I will later on introduce you to the team who has developed also the AI algorithm, and who is doing the quality inspection and the decision making. So here is an overview of the analysis of the USB, if it is printed correctly. So you see here the peak position is correctly detected. Give me a few seconds for that. This is the position of the AGV which is parked, and the Basler camera is focusing on the bay. The product will slide in. The analysis says that it's 100% correctly, so the robot is now picking it up. And you will see the robot slowly moving away to give it on the delivery station. Okay, that is all from my side about the animated journey of this use case. And I would like now to pass on the floor to Josef to explain to you a little bit more about the network infrastructure and also the test activities and the performance results we have achieved so far. Ever since our last delivery report last year, we have also proceeded some optimization activities, and also Josef will explain to you more about this.
So now let's go to the next part. And the next part, I have the pleasure to present some measurement results, and also what we did with respect to Profinet over 5G here. In all of the reports, what Georgios has already explained in 5G-SMART, also in 5G-SMART working group 5 meetings, we regularly report the update and the progress of all of the test beds. And what we have installed in our environment here is a fully standalone network operating in the German industrial campus band 3.7 to 3.8. We have used 80 megahertz bandwidth for these tests, and the test was mainly to analyze what is the performance of different network devices and what is the performance of different settings in configuration in the 5G system. The 5G system is based on a Huawei lamp side product elements here, and we have here mainly let's say 4 or 5 different radio heads distributed in the area, and in the test area it's connected to optical hubs, and then it goes to the 5G base station, because actually we have only one central base station, and the radio signal is distributed over the area in a distributed manner to have 100% coverage everywhere, and to guarantee that we get the performance what we expect here. There's also a connection to the mobile robot, what you have seen already in the previous presentations, and this mobile robot here has an own controller inside. That means it's a bit autonomous, but only a bit autonomous, because it's not really smart. It's just operating the arm and operating his own movement by itself. Then there's also connection to some edge stations to do the edge-based computing of the video mainly, and also a possibility to connect specific hardware what performs artificial intelligence-based analysis of the video clips. If you now go to the next slide, wait a moment. This shows in detail a bit more what we have. The Basler was already explained by Georgios, and thanks to this cooperation here, we have really the opportunity here to test different industrial cameras and for different purposes. We have also tested different industrial devices. It's a Huawei CPE, what is our reference device, because it has a best performance, and we know the performance of the antenna system, what is embedded here. Then we have different industrial devices. One is from LiDAR, but also different others, because our idea is and our target is to compare the performance of different devices with different antenna systems embedded or maybe also added by different external antennas here, as you see on the picture here, because this is important for a real deployment in a real customized way to our customers. Yes, so data rate what we have used here was 67 megabit in uplink, and for the video stream, but we have also tested with iPerf what we can get in a maximum. It was 120 megabit in this configuration here, and the video-based analysis you have already seen here in the video what is presented by Georgios. Now the next slide is presenting a bit our methodology, how we did the test. As the latency is always measured between the server and the CPE, but it's somewhere, maybe as an example, placed on a robot. The player, we have measured also player, and this is a block error rate in our definition here, and it counts missed packets at the end. Missed packet means packets not coming in time, and in time is very important because we have a deterministic network. Round trip time, for sure, it's a closed loop control reference here, because it shows how fast we can pass packets at the device back to the it's important also the round trip delay gives a certain indication how your cycle time can be adjusted, because this is a minimum delay what the 5G closed loop control system can provide to you. And the throughput, for sure, it's measured between the Linux server and based on TCP, but also in UDP. Now I go to the next slide. Hopefully it works. This shows the performance. Uwe, can you see the performance figures?
Not yet. Still on. Now it's there.
Okay, good. In here we have also done some measurement, as explained before, and one of the measurement was here based on the TDD configuration of our network, because it's for sure a TDD-based network. That means we are using only one frequency band with 80 megahertz bandwidth, as explained before. So uplink downlink adjustment is 4 slots are for downlink and 1 slot is for uplink. This defines a bit the capacity in downlink and uplink, and as a configuration is here done because it's minimize also the interference to cells outside of our campus. The ping delay, the maximum ping delay in round trip, that means forward and back, is 14 milliseconds. What you see here in the graph on the right side, the average is 6 to 8 millisecond round trip. Be careful with the measurement because it defines the data goes to the device and back from the device to the cloud. And this is a quite impressive time because actually it's 4 milliseconds one way. As throughput was in our measurement, as explained before, roughly 130 megabit in maximum. But we have done some optimizations because with this tail, what we see in the delay measurement, what you see maybe on the left side, with this tail, nobody is happy in industrial deterministic communication because it says that we have some packets are really delayed in the network and you don't like this. Then we did some optimization here in our configurations of the 5G network, and with different steps of the configuration we could achieve that we have no delay anymore. So that means no unexpected delays. Let's say we have really no tail in the delay graphs here. So that means no packets what come too late. We can define here in a very clear manner that we get all packets are latest in 10 milliseconds. And this is still, the round trip delays. That means one way, 5 milliseconds, forward and back, 10 milliseconds. This is a quite good number here, what we could achieve with a network that is really 16 compliant, but the device, and this must be known very clear, the device is still release 15 as a 3GPP release 15. Regarding this, I would like to ask you some questions here, as usual. For sure, you can always use a Q&A to add more questions to me, but and to our team. But here in the opinion poll, I will ask you. We have here in 5G ACA defined two different ways how you can connect robots or machines or AGVs. One is going from the assumption, starting from the assumption that all of the controllers are connected to the cloud and edge computing system, and in this way, they are connected to the 5G core network. Another opportunity or another way how you can connect your machinery is you connect it to the CPE. That means the data goes from the CPE because the controller is connected to the CPE up to the base 5G system and back to the devices. That means you have 2 times the radio system in use. And now I would like to ask you as an expert, and mainly you are the OT community here in the call, what is your preferred connectivity mode? Is it A, from the edge computing down to the device, or is it, yeah, I see already the result, thanks. That means here we see that both options are in use and both options are desired from the feedback what we get right now. Thanks a lot. Very good, very good. Then if we go further with the presentation here, we have actually it's a control to control use case. What we have is a robot. Now I go to the robot case and to the Profinet case, and the controller is still in the factory cell. But in this case, the controller is also connected to the UE, as on the CPE actually, what we see on the graph, on the diagram on the right side. The Profinet controller is connected via, let's say, a port mirror-based Profi-Shark equipment, because here we want to see the online traffic, the continuous traffic of all packets, and to monitor it. So we have a certain behavior in the Profinet communication pattern and traffic pattern. Then it's connected to UE, to a CPE. We have many CPEs in place here for different tests, and it goes over the 5G network. It's mirrored down from the 5G network core network over the base station down to the controller in the robot here. And this is what we have in place here for the mobile robot control, and both PLC controller and AGVs are connected to CPEs. And actually, they have to pass 2 times the radio channel up and down, and gain back if you have a closed loop. And each packet use uplink and downlink radio for the communication for the control also. And knowing this, we can still go to the next slide that shows a bit more that we really did it. Here you see on the screen we have a big display wall here, and you can see what is used with Profinet here. It's a configuration screen, and you can see Profinet is used with the Festo system, what we have here in place. And here you see on the next video here, if you see it, how we connected the Profinet Profi Shark let's say sniffer here into the line. On the left side you saw the Profinet controller, and here you see the CPE on the top, and in between we have the Profi Sharks. That means exactly what we have explained in the slide. You can see this is a monitoring tool what we have in order to track all of the Profinet packets on in real time. Actually, we can here analyze which packet is delayed, which packet is missed, and which information in the Profinet context is, or packet length actually is transmitted properly and in time. And here on this exactly the middle one, please click on it. You can see here also what we did with the traffic analysis here in real time for the AI-based observation of the objects and monitoring of the objects. And please on the upper middle one, yes, you see the, please click on the upper middle one. Here's that is how we did the setup. It's in the production line. In the production line there's a controller, there's a CPE, but also the CPE is on the upper side, and the lower side shows this real-time controller, real-time packet monitoring system, what we have used to catch all of the packets in a very, very precise way, not depending on the computing quality of a laptop or of a computer. It's really a real-time monitoring system. Please go to the next one. Yeah, now at the end of my part of the presentation right now, we are happy to perform this test on behalf of 5G ACA and to report this also to 5G ACA. As I said, the network what we have in our Ismaning Open Lab is release 16 based, but unfortunately we have at the moment not really a lot of CPEs or UEs or devices that can follow this standard here. We will still continue with the comparison of different devices here. We will also continue with the validation and the performance test of the use case 1, and for sure we are open to invite any of the any interested people or companies. We are happy that Basel has decided to take this opportunity here, and yes, what our in motivation is, we want to show that in this defined test environment that you can perform with your application as expected. And we have everything under control. So that means all tests can be really analyzed in detail. Then I would like to go to the next. Yes. I would like to ask you a simple, did you know already that 5G ACA has offered this kind of testbed to interested members of 5G ACA? And for sure, if you are a member, if you become a member, you're also invited to do it and to join our testbed. Oh, okay, it's a good feedback. Almost half or more than half of the participants has known this opportunity to join these testbeds. I don't talk only about the Huawei testbed, also other testbeds, and but still 40% or 44% of the audience here has never known it, and now you know it, and you are really invited to join 5G ACA in our testbed activities. Now let's go to the lab, because I would like to hand over again to Georgios and the team to show you what we really have in operation in live. Giorgio, can you start?
Yes. Hello from the Open Lab. It's good that almost half of you knows that you can onboard our testbed and our Open Lab. I'm taking this opportunity to emphasize that you can always contact us to participate on the optimization of use case 1 and the next use cases for this testbed, but also exploit the Open Lab facilities for other initiatives that are going on here. I can give some examples of other activities that are going on. We have AGVs that they have embedded cameras that are used to analyze the objects of the environment and do navigation based on artificial intelligence and object recognition. Many more initiatives that we can always come and join. And without further ado, I would also like to introduce Professor Jürgen Rodepas and our technical leads in the team, Kirill Friedman and Vincent Helfre. We are here in the Open Lab to give you a little bit of a preview of what's coming up next in the next use cases. And the floor is yours.
Yeah, thank you, Georgios. Thank you, Josef. Welcome to the Open Lab testbed. What we have seen in the previous videos is the quality inspection of the processes where the mobile eye, I call it mobile eye, is attached to the robot to check the process. But we can also optimize the transportation time, as Georgios said, because it is considered to be dead time. We can use this time to inspect the product. Now, in the next step of the next reporting period, we are going to install this mobile unit. It's a CPE and joint labs, joints here, connected camera from industry cameras, in that case from Basler, to attach it to the station number 4, where we can see the product itself. And the quality inspection here is to inspect the label and the size of the plug. How are we doing this? The video data are sent to the edge and being deployed and analyzed on the edge. So we don't send the data to the cloud, instead we do the opposite. We send back the pre-trained algorithm to the edge and to run the algorithm there. And this is the most interesting part, because this is part of a 3-year project in the Gaia-X environment we do with the University of Kaiserslautern, Smart Factory, and DSKI. And what are they doing? They are developing the pre-trained algorithms based on the basic set of data and send it back to our edge where it is executed. So we don't send the data to the cloud, we do the opposite. We send the software to the edge to be running over there. And this is very good because we can stay, the data can remain on premises here, and there's no violation of property. And the second advantage is that we can scale this use case across the partners sharing this individual production scenario. Because the different partners are working on the same production on customized USB sticks varying in shape, form, material, color, but having the same inspection task. So we can scale this use case. And this is very interesting for partners that will join here and maybe support us on this journey. So thank you very much. I go back to Josef or to.
I think the floor is back to Josef and Uwe. If there are any questions.
Maybe thanks a lot for this short overview of the next steps. I would like to give back to Jackie and to Uwe because we are already a bit over time.
Mm-hmm. Yeah. Thank you very much to all of you for the presentations and this live demo. So we are already over time, but I said we'll take a few questions, and I saw that we have at least 2 already in to all of you on the question and answer session. So there was a first one, I just read it, and this is a very generic one. So let's see who wants to answer. Is from the chat, is the business case for moving to 5G easy enough to demonstrate in your use cases? And if so, how is this being quantified? So that's something, I don't know who wants to start, if somebody from first group or second group wants to talk about this. So can you say already something that the business case is already there, or you need more time, let's say?
I think from our side, at least, I mean, we're not looking into business cases as such, since we are from a research, coming from Ericsson research. However, we are taking together with OT partners this first step into really taking some of the production KPIs into consideration. So we are looking at productivity, quality, safety, and aspects like this. So this is an input, I would say, to building the business case.
Mm-hmm. Maybe I can fully second Leefke's statement. Actually, our target is to enable business cases, and we are happy to work with companies together. That's some task and intention of 5G at all, to identify how can we help as a vendor of equipment to ensure that our partner can earn money actually. And the test what we did here with all of the test beds shows the capability of the 5G network, and based on this, business case can be developed further.
Good. Thank you very much. And then a second question which came in, also a more general one, is about the base stations you're using there. So what kind of base stations are these? Microcells, picocells, and so on? And how many stations are used there? And is there, what is the power demand? So about what kind of stations you're using there in the floor? How many are currently installed, and is there any indication of the demand of power consumption, I would say?
Vincent can explain if you want how many base stations we have here. In the Open Lab, we have 2.
Yes. So we use the land-side base station. So it's
Closer.
So it's indoor base station, which are well suited for these use cases. It's very much lower power than macro base station.
It's the lump side solution. It's part of the digital network solution of the product portfolio of Huawei that we have here.
Okay. Thank you.
From Bosch side, I can say that in our plant we use Ericsson's indoor radio delta system. Yeah, so we have in total 16 base stations. So we have 2 cells and 8 base stations per cells.
Good. Yeah, thank you very much. I would say to all, as we are quite over time, I'm not seeing that there's also another Q&A inside. I would say we would close here as we 5 minutes over time. And I'd like to thank you again for all the participants, panelists, the people in the lab live. So it was something different than compared to the previous ones. So thanks again very, very much. And there's an information for everybody, is that slides, and this will be made available afterwards. You get the information. And here's the input for the next one, the next web seminar, again about test beds, February 9th. In this case, European time, CT in the afternoon, where we hear more about industrial robotics and 5G Industrial Campus Europe work, again about the status and how far we are. So thanks again, everybody, for your participation, to the presenters, live demos, to the participants. And yeah, last word is, yeah, please join us again. As said, for the next web seminars. You see here also on the website you can find this, and also in LinkedIn as well as on the web. So please promote if you're interested, also to other colleagues. Thanks a lot for joining today, and have a nice day or evening wherever you are joining from. Thank you.
Thank you very much. Goodbye.
Thank you.
Thank you. Bye-bye.